Hi. So this will be the final video in our course. We'll look at several integrations where we have to take advantage of reduction formulas. We'll probably not find this in standard textbooks, but we will discuss these. Like these are very interesting, and I will show you a general method by which you will do these integrals. Okay. So the first integral that we'll look at is integrals of this form where you have x power m minus 1 a plus b x power n whole power p, and there is no standard method to do this. However, if we are able to get a reduction formula for this, by reduction formula what I mean is, can we connect this integral to an integral where the value of these powers are lower, right? Then obviously if we get the reduction formula, then we can write this integral in terms of smaller integrals. And eventually if you get a situation where you just have, say, a plus b x power n power 1 or some power, and x has disappeared maybe, then this is an easily integrable situation, right? So the idea is to be able to say that this integral can be written in terms of integrals where the powers m and p are slightly smaller, right? So how do we do this? So first of all, what we'll say is we'll do this substitution for now, and we'll look at this integral. X is equal to this, right? So just because we want to write the things in a smaller and concise manner. So what to do here? I want to connect this to the integral x power m minus 1 multiplied by x capital X power p minus 1 dx, right? So I want the reduction formula for this, and I want to connect it to the integral where p has been reduced by 1. M minus 1 is staying the same, right? So here is the general rule. The general rule is this. So in order to connect an integral like this, x power m minus 1, x power p, to another integral, x power m minus 1, capital X power p minus 1, right? What we take is we take a new variable, say capital P, and capital P expression you construct like this. You take x, and what powers do you assign to that? The lower powers, like in these two expressions, whatever is the lower power of x. In both the cases here, the power of x is m minus 1. So what I will see is lower power is m minus 1. You add 1 to it. So m minus 1 plus 1, and capital X, what is the lower power of capital X here? It is capital P, small p, and p minus 1. So it is p minus 1 is the lower value, so you'll add 1 to that. So my capital P has been constructed, and this is x power m capital X power p, right? Now once you have this, what we will do is we'll differentiate this. This is similar to the previous section where we do dp by dx, and from there we started doing things, right? We started writing it in terms of integrals. Let's differentiate it. It will become mx m minus 1 capital X power p, capital X power p, plus x power m small p into capital X power p minus 1 multiplied by d capital X by dx. Notice that capital X is actually this thing, right? So we get this expression. Now I will simplify this further. So you have dp by dx is equal to, just writing this in a simplified manner, it is mx m minus 1 capital X power p plus x power m p capital X power p minus 1 and d capital X by dx. And since capital X was a plus b x power n, you have d capital X by dx is equal to uh, nb x power n minus 1, right? So we can put that here, nb x power, this thing we can put it here, and we will get dp by dx is becoming equal to mx m minus 1 capital X power p plus p bn. Bn comes from here, x power m plus n minus 1, m plus n minus 1 multiplied by capital X power p minus 1, right? Great. Now, what we will do here is write this as this dp by dx will be equal to, now m into, we'll rewrite this as it is, x power p, plus we will write this expression as pn x power m minus 1 multiplied by capital X minus a, right? And x power p minus 1. Why? Because capital X minus a is actually b into x power n, right? And if you multiply b into x power n here, notice this is what is left. Basically, I'm just taking out b into x power n from here and writing it like this, right? So once you do that, you can rearrange now and write it like this: m plus pn x power m minus 1 common, and it is capital X power p, minus apn x power m minus 1 and capital X power p minus 1, right? This is your dp by dx, right? And now you can easily say that integrating this, notice that in both the expressions, you have small x power was m minus 1 and capital X power was changing. It was p and p minus 1 here. Now you just integrate this, you will get p is equal to m plus pn, and this is integral of x minus 1 capital X power p minus apn, this is integral of x m minus 1 capital X power p minus 1, right? Now this was your initial I, right? This was your initial I. So, and this was your I which was reduced, right? So what we can say is my reduction formula is becoming, I will just write it here, reduction formula is becoming p is equal to m plus pn I, which was m minus 1 comma p, minus apn I, which was m minus 1 comma p minus 1. So basically p is the expression that we only constructed, so p is coming as equal to this. Now you can solve for this from here, right? Bring it to the other side, divide by m plus and pn and so on. So this question right now we have done in a very general sense. We have taken no constants, nothing. We have just derived the reduction formula by taking all of the in general case, right? So what I will do now is do some examples where you will see the method being applied, right? So for example, let's see. Question 1 is finding this integral. I is equal to integral of x square plus a square to the power 5 by 2, right? This is a very standard looking integral. The problem is that this is 5 by 2, right? So what I want to do here is I want to connect this I 5 by 2 to I 3 by 2, which is integral x square plus a square power 3 by 2 dx, right? Great. So, and after that, I will connect this to root over x square plus a square, which is power 1 by 2. And this is a standard form. This is standard, right? So in order to do that, what I need to do is basically say that this integral x square plus a square power n by 2 needs to be connected to the integral x square plus a square power n by 2 minus 1, right? If I can figure this connection out, then my question is done. So how do we do that? So notice here, there is a 1 here, right? 1 in both of the integrals. So we can write this as x power 0, x square plus a square power n by 2 dx. And we have to connect it to x power 0, x square plus a square power n by 2 minus 1 dx, right? So what will be my p? Let's construct our p. So our p will be, in both of these factors, we'll take the lower power and add 1 to it. So lower power for x is 0 and 0. So you'll put x power 1. And what is the lower power of x square plus a square, it is n by 2 minus 1. So we'll say x square plus a square power n by 2 minus 1 and add 1 to it, right? So my p becomes x into x square plus a square power n by 2. Now, what we have to do is differentiate this and try to write it in terms of, let's call it in and let's call it in minus 1, right? Correct. So let's see how we'll do that. So let's see what happens if you differentiate p. P is x into x square plus a square to the power n by 2. Therefore, dp by dx will be equal to x square plus a square power n by 2 plus x into n, you have n by 2 into x square plus a square power n by 2 minus 1 multiplied by x. X was unchanged and x square is integral is 2x differential. So you get this thing. So your dp by dx is becoming equal to x square plus a square to the power n by 2 plus n times x square multiplied by x square plus a square to the power n by 2 minus 1. And this thing we can write as x square plus a square power n by 2 plus n times x square plus a square minus a square, right? And whole thing is multiplied by x square plus a square whole power n by 2 minus 1, right? Why did I do that? Because I want powers of x square plus a square, not some x square alone, right? So dp by dx is now becoming, this into this will be n by 2. So you have 1 plus n plus 1 into x square plus a square to the power n by 2. And you have minus na square x square plus a square power n by 2 minus 1, right? So this is my dp by dx. Now we are almost done. We are ready to actually solve it. We'll say integral of dp by dx will be p. P will be equal to n plus 1 integral of x square plus a square power n by 2 dx minus na square integral of x square plus a square power n by 2 minus 1, right? And what was p? P was x into x square plus a square power n by 2. This is equal to n plus 1 into your I initial minus, we can call this n by 2, minus na square I n by 2 minus 1, right? So now I get the formula for my integral here, right? This integral is evaluated now in terms of this, right? So I will write it on the next page. So we have integral of x square plus a square whole power n by 2 dx is coming out to be x into, this is your p term, divided by n plus 1 because there was n plus 1 here, plus na square by n plus 1 integral of x square plus a square power n by 2 minus 1 dx, right? So this is now doable. Now put n is equal to 5. You will get the formula in terms of, here it will be 3 by 2. This will become x square plus a square 3 by 2 here. And then put n is equal to 3. You will get it in terms of integral of root of x square plus a square. And this is a standard result. So you will work back, you will get the formula for I3 and I'll get for I5, and that will be the answer, right? So this was one example where we applied this. So another example that we can look at here is, for example, this question. Let's say we have this integral. Calculate the value of 0 to 2a, 0 to 2a, x power m root over 2ax minus x squared dx, right? M is a positive integer. M is positive integer, right? Okay. So what I want to do here is again connect the integral, this one, 0 to 2a x power m root over 2ax minus x square to the integral 0 to 2a x power 2m minus 1, or x power, it was m, so x power m minus 1 root over 2ax minus x square, this integral, right? So how do we do that? First of all, you can write this as 0 to 2a. You can take x outside here, right? It will become x power m plus half, and it is root over 2a minus x, right? And we want to connect it to 0 to 2a x power m minus half root over 2a minus x, right? Okay, so how do we do this connection? Again, we'll follow the rule where we construct a p, and p will be composed of two factors. One is x, one is root 2a minus x. And what are the powers? So we take x, we take the lower power is m minus half amongst m plus half and m minus half, and we add 1 to it, right? We'll say that it becomes m minus half plus 1, which is m plus half. And actually, we don't need to put an integral. We're just constructing the p function here. And multiplied by 2a minus x. Now 2a minus x, both the cases the power is half, so we'll add 1 to that, and it will become 3 by 2, right? So this is my p function that I have constructed. Now I'll differentiate this p, and I will be able to write the answer in terms of this integral and this integral, right? So let's see if it works out or not. So p is equal to, for us, x power m plus half and 2a minus x power 3 by 2. So what is your dp by dx? dp by dx will come out to be m plus half x power m minus half and 2a minus x power 3 by 2 and minus 3 by 2 x power m plus half and 2a minus x power 1 by 2, right? This is the differentiation. Simplifying this a little bit, dp by dx will become equal to 2m plus 1 by 2, 2m plus 1 into 2m plus 1 into by 2 into this. So what we'll get here is, I think we have to take root 2a minus x common here. Yeah, I think what we do is take root 2a minus x common. 2 minus x common. So now what we have is m plus half multiplied by x power m minus half multiplied by 2a minus x minus 3 by 2 x power m plus half, right? So simplifying this, you get 2m plus 1 x power m minus half multiplied by 2a minus x divided by 2 minus 3x power m plus half divided by 2, right? So we get 2m plus 1 into 2a by 2, you get 2m plus 1 into a into x power m minus half minus 2m plus 1 into x power m plus half by 2, and we get minus 3 by 2 x power m plus half, right? So simplifying that, what do we get? We take minus x power m plus half by 2 common, we get 2m plus 1 plus 3, so that is 2m plus 4, and that will be m plus 2, right? This will be equal to minus m plus 2 x power m plus half, right? So finally this whole expression has become this thing and this thing, right? So I can write this whole expression now as 2m plus 1 a x power m minus half multiplied by 2a minus x power half minus m plus 2 and x power m plus half multiplied by 2a minus x whole power half, right? This is the final expression after simplifications, right? Now, notice that we can easily say that I will isolate this part. This part I will isolate and I will bring it to this side. So what I will get is m plus 2 integral of x power m plus half multiplied by 2a minus x whole power half dx should be equal to minus x power, so p goes to the other side, minus x power m plus half 2a minus x power 3 by 2, right? This is p going to the other side. After I have integrated, it becomes, instead of dp by dx, it is p, and plus 2m plus 1 multiplied by a integral of x power m minus half into root over 2a minus x, right? So this is the expression that we are getting. That just tells us that if I integrate this now, 0 to 2a, right? This part becomes 0 to 2a, and I can take x power half inside. So it will become x power m root over 2ax minus x square dx is equal to this integration. We have minus x power m plus half 2a minus x whole power 3 by 2 divided by m plus 2 evaluated from 0 to 2a plus 2m plus 1 divided by m plus 2 multiplied by a an integral 0 to 2a x power, this is m minus 1 because now root x goes inside, and root over 2ax minus x square, right, dx. So notice that this integral that we wanted to find is now coming in terms of this constant value plus this integral which has x power is diminished, right? And everything else is same, x power has reduced, right? So we can easily find I of 1, I of 2, and so on, right? So when m is equal to 5, you can find a formula to connect it to m is equal to 4, and so on. Now, this method that we have seen so far is not just useful in algebraic equations, it is also useful in situations when you have sine and cos powers, right? So now I'll show you the generality of this method. So this is, let's think about what to do when you have to find out the reduction formula of this, right? This is my integral that I want to find out, and I want to connect it to this integral of sine of p minus 2x and cos of qx. So you just want to reduce the sine part, you want to keep the cos part as the same, right? So again, here also we'll construct our p, and the rule for making our p function is the same. Take both the factors, take the lower power in both of them, this is p minus 2, add 1 to it, so it will become sine of p minus 1x. Take cos, what is the lower power? It is q, add 1 to it, so cos of q plus 1x, right? Once you have constructed this p, do dp by dx. dp by dx will be equal to p minus 1 sine of p minus 2x cos of q plus 2x minus q plus 1 into sine px multiplied by cos qx, right? So this simplifies as dp by dx is equal to p minus 1 sine of p minus 2x cos of qx, and cos square x is left, which we can write as 1 minus sine square x minus q plus 1 multiplied by sine power px cos power qx, right? And this can be further simplified now as p minus 1 sine power p minus 2x cos power qx and minus p plus q. We are adding p minus 1 from here to this. P minus 1 plus q plus 1 is p plus q. And you get sine power px cos qx. If you're not convinced of this step, just check your calculations again, expand everything here and expand everything here and see what happens, right? It will come as this. And now we can easily say that integrating all sides, you get p is equal to, you have p minus 1 integral I, where sine power is p minus 2, cos power is q, minus p plus q, where the integral is I pq, right? So therefore, I pq is coming out to be equal to p minus 1 by p plus q, I p minus 1 comma q, minus 1 by p plus q into capital P, right? Right, and capital P we know we have only constructed it like this. So I want you to see one or two examples at least where we use this property. It should be very clear how we'll get it. So let's actually find out the case when you have integral of sine power nx, right? Sine power nx dx. So in general, we had seen the case when it was p and q, right? Now we are saying that one of them has disappeared. Q is 0, right? So we'll connect it with integral of sine n minus 2x dx, right? So let's construct our p. We'll imagine that there are two factors, sine and cos. Cos is basically 0 powers in both. So we'll create cos 0 plus 1 is the lowest power plus 1. So cos x, and this is sine of n minus 2 plus 1. So n minus 1x, right? This is our p here. So dp by dx will become equal to n minus 1 sine n minus 2x cos square x, because sin x differentiation is cos x, minus sine power nx, because cos x differentiation will be minus sine x, and it will add to this, right? So simplifying this a little further, you get n minus 1 sine power n minus 2x minus n minus 1 plus 1. So n times sine power nx. That is your dp by dx right now, right? Now, once we have this, therefore, we can say that n sine power nx is equal to n minus 1 sine power n minus 2x minus dp by dx, and therefore now we can say that integral of sine power nx is coming out to be n minus 1 by n integral of sine power n minus 2x dx minus p, which was cos x. So we get n minus 1 by n into cos x into sine power n minus 1x, right? So this general method is useful to us because we are able to find the reduction formula for sine also, just sine power nx, right? Now, similarly, you can find reduction formula for cos as well. And if I wanted to find the actual limit here, like actual definite integral here, so let's say you have a definite integral s of n is equal to 0 to pi by 2 sine of n of x dx, right? If we have this definite integral, then because the reduction formula has this term sine of n minus 1x cos x, right? And this term will vanishes at both x is equal to 0 and x is equal to pi by 2. Therefore, once you apply the definite integral, your Sn will simply be equal to n minus 1 by n s of n minus 2, right? Because the second term in the formula that we just discovered in the previous screen is vanishing. This term is vanishing. So s of n minus 2, and now we can write that as n minus 1 by n, and instead of n, I'll put n minus 2, I'll get n minus 3 by n minus 2, right? Which is s of now n minus 4, right? And similarly, going forward, one more step, if I go forward, you get n minus 1 by n minus 3 by n minus 2, multiplied by n minus 5 by n minus 4, s of n minus 6, and so on, right? If your n is even, you'll eventually get Sn is equal to n minus 1 by n multiplied by n minus 3 by n minus 2 multiplied so on 5 by 6, and then it will be 3 by 4, then it will be half, and then finally it will be s of 0, right? S of 0 will be integral of 0 to pi by 2 1 dx. So you will get the formula Sn is equal to n minus 1 by n minus 1, n minus 3, and so on till 5 3 1 by n minus 2, and so on 6 4 2 multiplied by pi by 2, right? And if your n is odd, in that case you will get this situation. If n is odd, you will have S of n is equal to n minus 1 by n into n minus 3 by n minus 2, and so on till 4 by 5, and then 2 by 3, and finally you will have S of 1, which will be 0 to pi by 2 sine x, right? And the value of this is actually equal to 1. So your formula will end at 2 by 3 if n is odd. S of n will be this, right? 4 by 5 to 2 by 3, right? So this is the value of your integral, definite integral for s, where it was sine power nx, right? 0 to pi by 2 sine power nx. How did we get this? We first got the reduction formula for sine power nx, and we followed the method that we have seen. When there are two factors, something x power m minus 1, x power p, and you have to connect it to an integral x minus 1 and x power p minus 1, then we construct a capital P where we say x is x power m and capital X power p. How do we construct both the factors? We take the lower power and add 1 for each factor. So here m minus 1 plus 1, and x here lower power is p minus 1, p minus 1 plus 1, right? Once you do this, you can differentiate this, and then you will get the connection between this integral and this integral, right? And we are applying the same principle even for the trigonometric ratios, right? The formula is the similar formula. If you have an integral 0 to pi by 2 cos nx, right, dx. Again, for n is even and odd, the formulas are the same. If n is even, you will get the pi by 2 at the end. And if n is odd, you will get 2 by 3 into 1, right? So one nice way to remember this formula is, like, if I have to evaluate this integral, it is either sine or cos whole power nx dx, right? What you can say is each of the formulas can be written by beginning with the denominator. So you will say n minus 1 by n, that is the first term in both the formulas, and then n minus 2 by n minus 3, right? N minus 3 by n minus 2, n minus 3 by n minus 2, and so on. You keep going till you either get 2 by 3 if n is odd, or you get, or the other cases, you will get 1 by 2 if n is even. And if n is even, you will not stop here, you will multiply by pi by 2. And if n is odd, you will stop here, right? So this is the way to remember. Start with n minus 1 by n, subtract 2 from numerator, denominator, keep going till you will have to stop at either 2 by 3 if n is odd, and you'll have to stop at 1 by 2 if n is even, but multiply by pi by 2 in that case, right? So that is your reduction formulas. We can discuss more here, gamma functions and all, but I will leave that for now because I don't think that is required for JEE Advanced. even this class, whatever we have discussed, is probably too advanced for JEE, but I just wanted you to know so that you know a standard method to handle all of these reduction formula cases. So if you have any confusions, go through the video once more, pause and think. And if you have doubts, you can always reach out to me on the YouTube channel as well as on the website. So just try to get this idea here, the idea that we discussed in this class. It's a very general idea, the reduction formula by that constructing a P function, that method. So go through the examples once more if you have any doubts and let me know if there is any difficulty. With this, we come to the end of the course. I will be creating more and more courses for JEE as well as for Olympiad. So check out the website, keep learning, and best of luck for your exams.